So I've been trying to make this talk shorter because it usually goes pretty long every year. It still will probably be long. If you need to leave, you can leave anytime. You can talk, you can, whatever. This can be informal. But I have a lot to share even though I've culled it down. So stop me if you have questions, leave if you want to leave, etc. But this is kind of what I want to cover today. I'm just trying to tell this is sort of designed for the guides around here and people in that same sort of boat, which is like, what's the stuff that you could share with people who are coming here? Maybe, I know a lot of you know a lot of stuff, probably a lot more than me on a lot of things, but some facts and figures, the stories of this place as I know them. And so I'm going to start with kind of like classic geology, right? Like the tectonics, how this place got here, a little bit about the bedrock. That's not my specialty, but a little bit about how the copper got here because people care. And a little bit about the volcanoes. I'll kind of go through that stuff pretty quick. And then get into glaciers, which is actually what I've spent most of my time here working on. And in that, try to give you a little more sort of updated information, some of the latest things that we've learned. And not just questions. I know there's a lot of people in this audience who could add a lot to this. And so if anyone wants to raise a hand and correct me or add a little detail or whatever, feel free. So we're just going to start with the biggest possible big picture, at least in my mind, for this place, which is plate tectonics, and how southern Alaska got here. If you don't know, if you didn't take like basic geology, the thing to know about plate tectonics, which is sort of like continental drift, but continental drift was the old idea, plate tectonics is the new one. This is just like a little cartoon, but the important thing about this that you need to understand is this is showing you kind of in an exploded form the boundaries between some tectonic plates. That's Africa, of course. And the thing I want you to notice is that the continents aren't floating around on the oceans. The plates include the oceans. The bottom of the ocean floor is moving around and is part of a plate along with the continental crust. So we have like oceanic crust and continental crust. And like in this case, they're part of the same plate and they're moving around together. In this example, there's a boundary between oceanic crust and oceanic crust. But sometimes, like up there, there's boundaries between, sometimes the plate boundary is at the edge of the continent, and that has some significance. And so we're gonna try to understand what the boundary in southern Alaska looks like. This is sort of a classic cartoon of what plate tectonics does to the surface of the Earth. This is just kind of what I explained here, that the Earth has a lithosphere of rigid plates, include the, like, blah, 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 we went through that. But the rest of that definition of plate tectonics is just explaining this little cartoon here. And the main thing is that you have magma that rises up in the middle of the oceans, usually, that causes plates to spread out, go sort of both directions. And then oftentimes plates run into other plates. In this case, this is oceanic crust smashing into continental crust, so they're running into each other like this. And it doesn't seem like it should be this simple, but it is, that oceanic crust is denser. The rocks are a little heavier than continental crust, so the oceanic crust goes down, it subducts. When they run into each other, the continental crust stays up on top because it's a little bit lighter. And when that happens, you're taking the crust down into this deeper part of the Earth where, of course, it's hotter. Everyone knows that from Bible school. And then it melts and you get volcanoes. So that's kind of like a classic subduction zone, is this collision, subduction, and then volcanism. And so you create new crust at the spreading centers, you consume crust at the subduction zones. I'm going to try to prove that to you with some data. So this is the western US right here, western North America we'll call it. Give a nod to Mexico and Canada. And it's again just kind of cartoon, big picture of the tectonic setting of western North America. We're of course up here in Alaska. This little toothed line right here, that's a subduction zone. That's where the Pacific plate, which is this big thing, is moving northwards in the direction of the red arrow, and it's running into Alaska, because Alaska sticks out off of the North American continent like a thumb. And so as the Pacific plate is going up next to it, it runs into the thumb and it subducts. That's the normal state of affairs. So southern Alaska is a subduction zone. Down here, this is complicated, and we don't really need to get into it, but most of western North America is a strike-slip boundary, meaning the North American plate is just kind of cruising alongside North America. And that does not generally create big mountains and subduction and volcanoes, although it will do some of those things. And of course, it does cause earthquakes. So the famous San Andreas Fault in California is right down here. And that's a major plate boundary fault right there. And why I like to start with this little cartoon here. Am I just like continually in your way?
That's okay, Mom.
You should just slide along. I don't want you like that. Okay. You sure? Okay, I'm gonna stand right here. You good, Brian? You good? Okay. I'm just trying to be a good host. Here's why this is a good place to start the story we're going to tell is because this part of California, sort of southern and central California coast, you can see here, it's on the west side of the San Andreas Fault, so it's actually part of the Pacific plate. It's not part of the North American plate. And as that strike-slip boundary moves along at about the speed of your thumbnail growing, that's about how fast these plates move, is about as fast as your fingernails grow. The Pacific plate is going up here and subducting underneath Alaska, but it's also carrying along every once in a while a chunk of continental crust that just, happens to be along for the ride. In this case, that's Southern California. Los Angeles is along for the ride with the Pacific plate. And if you look far enough into the future, it's a long time, and I don't know how long, but many millions of years, it's going to end up there. Los Angeles is coming here. And yeah, I know. When it gets here, it's a little chunk of continental crust, and you'll recall, is continental crust more dense or less dense? Less dense, all right, you guys are listening. I'm in your way again. And so it's not going to want to subduct because that little chunk of the Pacific plate is not heavier or more dense than Alaska. And so when it hits Alaska, something's going to happen other than a subduction zone, a straightforward subduction zone. That's coming. That's in the future for Alaska. And let me show you a little bit about the Alaska subduction zone. This is not a cartoon. This is data. I told you I was going to prove to you that subduction happens to counter the idea that the Earth is ever expanding. So here's Alaska, and what you're seeing here is every little tiny dot is an earthquake that has been measured and located not just in XY space, but in depth underneath Alaska over a long period of time. Little earthquakes and big ones, so lots of little ones. And what you can see is like red. See how on the kind of northern edge of this, it's mostly red. And then on the southern edge, it's mostly blue. And here's a good place to see that sort of transition from blue, green, yellow, red. Those are depths of those earthquakes. So blue is shallow, it's deep. 33 kilometers is pretty deep in the crust. But it's a lot shallower than 33 to 75 or all the way up to 125 plus kilometers. So what you're seeing is this is a ramp right here, and it's true here as well, of earthquakes going deeper and deeper down into the crust. And that is a direct measurement of the subducting Pacific plate sliding underneath at a dipping angle underneath Alaska, which is part of the North American plate. And so here again is a cartoon of a subduction zone, but this is real data that shows us that that's really occurring. So we have a modern day subduction zone in Alaska. For those of you who don't know, the Aleutian Islands are a volcanic mountain chain. There's a lot of volcanoes that pop off out there. We have volcanoes that pop off near Anchorage, in this part of south central Alaska. And as we'll get to, there's some volcanoes in the Wrangles, where we are, although they're a little more complicated. And you can just see that like the subduction zone, the trench is right here. And the whole subduction zone's quite narrow there, and it does look like it's different here, right? This is the Wrangels right here, going all the way into the interior, and it looks like it's dipping at a shallower angle, and actually, happily, there's a big seismic gap right there, right over where we are. We can be shaken by distant earthquakes, but there's not many earthquakes that occur right here. This is kind of a weird place, and I'm going to try to tell you at least part of why. Oh no, we don't want to talk about that. So here's again a little cartoon of what we just saw, but now I'm bringing in a little detail that's super important, and that's this little chunk right here. So again, there's the subduction zone. Here's southern Alaska, and what this is like Los Angeles. This little chunk is called the Yakutat microplate. It's right offshore of Yakutat, and it's more buoyant or less dense continental crust that was caught up way down in the Pacific Plate, way to the south of here a long time ago, and is presently smashing into the coast of Alaska just south of where we are right now. Not the whole coast, but just here where we are. And I told you that subduction zones don't really work very well when continental crust shows up because it's less dense. And so the best example of that sort of globally is the Himalayas. That's India running into Asia. It's all continental crust. And we all know, because most of you are mountaineers, those are big mountains, right? Biggest mountains in the world. And why are they there? They're there because it's continental crust collision. That's what we have happening right here, because this little chunk of continental crust that we call the Yakutat microplate is running into Alaska right now, and it's not very happy to subduct. And that's very similar to what's going to happen, let's say 100 million years from now, when that little chunk of California hits. But that's in the future. This is now. And I'm going to talk a little bit more about what that means for what's happening right here in the Wrangels in a moment. Does this make sense to everybody so far? With me? Okay. So here's the biggest possible picture of what that collision means for Alaska. There is that little chunk of the Yakutat microplate that is not happily subducting. Here is the normal subduction zone, but this is like a little miniature Himalayas that's occurring right to the south of us. And some of the highest peaks in North America, Mount Logan, Mount St. Elias, right? They're down on the coast to the south of us. The whole coastal St. Elias range is our little miniature Himalaya that is forming because of that collision right there. Really active uplift. It's giving rise to those mountains right now because of the nature of that collision. Meanwhile, all of the rest of Alaska and the Yukon around there is like trying to figure out how to get out of the way. And so there's mountains that are forming out here. I've never been to them. Has anyone ever hung out in the mountains like the Thompsons, I think, maybe, and the, I don't know, there's some mountains in the Yukon that, like, far away that are uplifting presently because of this indentation. And then this line right here, this is the Denali Fault. And see how it's got a big curve in it? And that's an active strike-slip fault where everything's being pushed this way, follow the arrows, by that collision. And if you have a strike-slip fault like this, and then you put a curve into it, so try to follow me here. Here's a strike-slip fault. If it's straight, there's not much mountain building. But if the strike-slip fault is bent like this, the plate that's going this way runs into trouble at the curve because it wants to keep going like that, but there's a curve, and it's kind of like when you don't make the curve on a highway and you get in a crash. Well, there's a crash, and who wants to guess what's at the curve on the Denali Fault? Denali, right? Exactly. So why is Denali so high even though it's not in our park? Because of what's happening in this park. The tectonic story of the Wrangels is what's making Denali so high. It's a far field effect of the tectonic situation here. And you can measure with GPS, and you can actually see that all of sort of western Alaska is being pushed even like 1,000 miles away, slowly to the west by this collision. Okay, so this is a big part of why there's big mountains on the coast of this park right now. And then to bring it even more local to like here, where we are, the Kennicott Valley, we can go back even further in time. So in the future, California will hit the California microplate, I'll call it. Right now we have the Yakutat microplate. We are sitting here on the Rangelia microplate. So in the distant past, let's say, because it's written right there, about 90,000 years ago, or maybe you want to start the story there, whatever. I don't have a good memory for these millions of years things, and who cares anyway. Long time ago, a chunk of crust came up on the Proto-Pacific plate and smashed into southern Alaska, just like the Yakutat plate is doing now, and that thing, which we can recognize because the rocks within Rangelia are distinct. They came from a certain place. And you can imagine that when the Los Angeles microplate shows up, its rocks will look different than the rocks here. And the Yakutat rocks look different. So you can tell when you're moving from one microplate to another because the geologic history recorded by the rocks is totally different. And so the Rangelia rocks, the ones that we're going to talk about in a moment here, they came up with their own particular history as a microplate that got stuck onto Alaska a long time ago and created its own mountain ranges at that time because of the collision. And the rocks we see now are the Rangelia rocks. And it's cool, this was cool for me, it might not be cool for you. I was just over in Burwash Landing, over in the Yukon, and I was with a geologist who knows that area well, and we were looking out over the Kaskawolsh Glacier, and he's like, oh yeah, that's the Duke River Fault there, that's the boundary between the Alexander microplate and Rangelia. There it was, the Rangelia rocks. And I was like, is there like, Nikolai greenstone in that mountain? And he's like, yeah, which is a rock that we have right here. If you go to those if you follow the microplate boundary, you'll stay on a geologic history you recognize. When you cross a boundary into a new microplate, it's a whole new history. And not only do I not know that history for most of the microplates, I would also probably find it boring because I'm more into glaciers. So we're only going to talk about the geologic history of this microplate and just a little bit of it so that we can talk about the copper. But let's just see, this is the outline of Wrangell St. Elias National Park. There's the southern coast of Alaska. There's Yakutat Bay, Icy Bay, and in brown there, Rangelia. There's Rangelia, and of course Rangelia, there it is, the Duke River Fault, see that? And the Denali Fault, where's Rangelia? This was made by some federal map maker who doesn't believe Canada exists. But actually Rangelia continues down there into Canada. But look at all these other colors. These are all the histories that we're not going to talk about, but there are all these other microplates that have this same story of smashing into the southern coast of Alaska, getting scraped off, and then another one comes. And so you can sort of infer that these are older and these are younger, and indeed, the Yakutat microplate, there it is. It's actively smashing into us right now. So that is, I think, oh yeah, and then there's this, the whole state of Alaska, and every one of those colors is a different microplate. So holy cow, it's complicated and mostly boring. So let's not talk about most of them. Let's just focus on Rangelia. I mean, look up there, like this is all flat, like who cares? But down here, Rangelia, that's what we're gonna talk about. If I'm not mistaken, I think right here is the only part of Alaska that is part of the original craton, they call it, like was part of North America before all this junk got stacked onto it. All the rest of this is like, it's like an immigrant story. These are all chunks of geologic terrains that got amalgamated over time. Okay, any questions about that? That's the story, as I'm telling it, of the tectonic history of this place. Yes, Jamie.
I just wanted to go back a couple slides.
Yeah.
Edit to the map one right after that one.
Yes.
So the Yakutat is that whole area along the coast, even though it's not colored outside of Wrangell St. Elias?
Oh, to the left? No, I think over there you're into, I want to say well, it's not I don't think that's part of the Yakutat terrain. Does anyone know? That's not the Yakutat over there. What I will say is the Yakutat terrain does come, well, maybe it does go to right there. What I know for sure, Jamie, is it comes well out into the ocean down here, and that's not being shown. It's underwater in places. I don't know if I don't think the Yakutat goes all the way to this fault right here, but does anyone know? Tim? It does. Okay, well, there we go. So it goes out to that fault boundary and well to the south. And there's a fault that runs down here called, I think, the transition fault underwater, and that's the boundary between that lighter, less dense continental crust and the oceanic crust. And that's where eventually the Pacific plate is going to break off and leave the Yakutat microplate behind and keep subducting. Any other questions? Yeah.
Is isostatic rebound exacerbating any of this, or does it have any play in how it's being pushed together?
Yeah, great question. So isostatic rebound, for those who don't know, is just the idea that at depth, underneath the crust, we have the mantle. The mantle is a little bit, it doesn't really flow like lava, but it's soft. And so if you push down hard on the crust, a lot harder than I can, that stuff will kind of ooze out of the way, like putting a ship in the water. And then when you take that heavy thing away, the mantle will come back and push the crust back up. And the main thing that's done that in our recent past is ice. As we'll talk about more later, there was big glaciers here. Now mostly they're gone. So we do have isostatic rebound. It's definitely contributing to the uplift, especially at the coast, sort of in addition to the tectonic processes I was talking about. You do have isostatic uplift. I don't think it's having much effect on the sort of lateral motions. Probably some tiny bit that someone would think of. But yeah, but there is definitely significant uplift, especially down by Glacier Bay, Gustavus, Yakutat, that area. Was there one more question? Yeah.
Do these different terrains have any effect on the kind of vegetation that grow on the land?
I think it's a great question. The terrain per se would not, but the bedrock that's exposed at so each of these terrains has a layer cake of different rocks that's unique to it, and whichever one of those layers is exposed at the surface potentially could have a significant effect. Like if you had a limestone at the surface, you would expect slightly different vegetation than a basalt. Although my experience as a former botanist is that in Alaska, the effects of different bedrock types are more muted on vegetation than they are in some other places that have more diverse floras. Here it just seems like willows will grow on everything, kind of thing. Other questions? Okay, we can come back. So briefly, the only thing more boring than the tectonic history of terrains out in the middle of the Yukon-Tanana uplands is copper mining. But you all have to talk about it, and so I will too. So I'm just going to give you the nutshell story of how the copper got there. We're going to use the bedrock history of this place to sort of tell that. I'm not a geochemist, so I'll quickly get over my head, but it is kind of a neat story, at least in broad outlines. So y'all know, like, lots of money was made here. We don't need to overdo it. This stuff here, the green and the blue, probably most of you know this. The green stuff is malachite, the blue stuff is azurite. Those are carbonate ores of copper. They're actually pretty low quality. They weren't the good stuff that the miners were going after here, but they are the prettiest. But in any case, let's just talk about, that looks like the same slide. Okay, let's talk about how that copper ended up here in particular, where it came from and where they found it, where they mined it. So this is a geologic map of our valley, right? There's the Kennicott and the Root. This is Bonanza Ridge running along here. There's a McCarthy Creek coming down and around. There's the hardware store. The main thing I want you to sort of pay attention to, because of course the mines were all up here above Kennicott. You can see them, these little picks and shovels, I guess. We have the light blue, the dark blue, and the purple. And those are like the layers within Rangelia that really matter for the copper story. So if we look down here, this is a stratigraphic column, meaning it's representing, at least theoretically, what rock layers are on top of which. The ones at the bottom are the oldest and they're lowest stratigraphically. The ones at the top are the youngest. And those colors we were just looking at, light, dark blue, and purple, they're right here. So they're like the basement rocks for Rangelia, at least in this area. They're the oldest rocks. And the basal one is this Nikolai greenstone. All these rocks get named for where they're first described. So Nikolai greenstone means some geologist first formally described that rock from an outcrop, probably, at Nikolai Plateau or Nikolai Pass. That's all that means. But the greenstone is talking about what kind of rock is it. And greenstone, it's not particularly green around here. It's greenish. Maybe I tend to think it looks more purple, but it's basalt. It's a volcanic rock that's been metamorphosed. And then on top of it are these two different kinds of limestones. So they're sitting stratigraphically on top of that. There's all this other stuff that you can see around here. Mostly, I'm not going to talk about those. But to show you a familiar site, right, this is Donahoe as viewed from up by Jumbo, and I think this is maybe from Glacier Mine right here. There's the limestone, the Chittestone limestone, and there's the Nikolai greenstone, which I said was basalt. And it's the darker stuff. And this is the contact. People talk about this like mythically around here, the contact. It's the contact between those two layers of rock. And it's mythical because that's where the copper was mined. And so what I just want to explain is, why is the copper there? Where did it come from, and why did they find it there? Why is that where they mined it? I will say briefly that, I'll just describe these rock types to give you a sense where they came from. The greenstone, I said, is a basalt. Here's a picture of basalt flowing on the surface in Hawaii. I think I didn't take the picture every time I've been to Hawaii, which is only twice. You couldn't really see it, which is too bad. But basalt is this like oozy, flowy, dark, volcanic material that often erupts out in the middle of the oceans. And in fact, remember that Rangelia started out in the middle of the ocean. I showed you that picture, and it was down in the middle of the Proto-Pacific. Probably Rangelia, unlike Los Angeles, the Los Angeles microplate, it appeared out of nowhere, so to speak, somewhere in the middle of the ocean by virtue of these volcanic eruptions that deposited a bunch of basalt, initially probably at the bottom of the ocean, and then it piled up, piled up, piled up. So it wasn't exactly like Hawaii. It wasn't probably a hot spot, but if you want to picture Hawaii like a big basaltic island in the middle of the ocean, that's a pretty good way to imagine the origin of Rangelia. Maybe not directly correct. So that's out in the middle of the ocean being carted northwards by the Proto-Pacific plate. And then once those eruptions stop, because this was down by the equator when this happened, we think, it was like a warm, shallow tropical sea, and limestone, which is a chemical sedimentary rock, started accumulating on top of it. And the very first layers that accumulated on top of the basalt, I'm told, are also forming in the modern day here out in the Middle East. This is what's called a sabkha environment. I don't know much about it, really, to be honest, but it's shallow, really warm, briny, mineral-rich waters sitting on top of our basalt and raining out the material that becomes this limestone. It's like calcium carbonate and a bunch of other stuff. Some of it's dolomite, whatever. That's where that next layer in our layer cake came from. And actually, several more of the layers on top of that formed out in the ocean before Rangelia ever hit the coast of North America and was amalgamated to Alaska. But we're just going to focus on these two, the Chittestone limestone that was on top of the greenstone. And this is a low quality, because it's old, figure from Ed McKevitt's paper, which is like the classic paper about how the copper formed. This guy was a geologist that was very active in this area, like, I don't know, in the 50s, 60s, 70s. He did most of the mapping. If you pick up any geologic map of this area, it was probably made by him. And this is his explanation, using a little bit older technology, so it's not as fancy, of how the copper formed, and I want to just walk you through it. So in this picture, we'll start up here. This is a very simple diagram. The dark stuff is the Nikolai greenstone, right? It's the basalt. And on top of it is the limestone. Okay, so that's the two layers we've been talking about. And the way this story begins is the basalt, remember it was lava, it had some copper in it. And you could ask me why, and I would say, I don't know, it's lava. It had all this stuff in it. Remember, plates get subducted, and they melt, and they get mixed around in the mantle, and I don't know. But just there was a little tiny bit of copper. There's lots of stuff in lava, in all lavas, and in that lava, 100 parts per million, that's what that ppm means. So there's not a lot. You're not mining the basalt and making any money. But that's where the copper in this area originates, is in the basalt. So what happens next in his little story over here, and I think, oh yes, caves form. Okay, so karst landscapes that have lots of caves, usually form in areas where the bedrock is limestone, because limestone is soluble in water. And so even if you're deep underground, there's this thing, groundwater. And so anytime there's cracks, there's going to be water circulating through there, unless you're in the desert. And you're going to gradually dissolve the limestone and create bigger and bigger spaces that will become caves in the right conditions. And in Ed McKevitt's history, this is all happening millions of years ago, deep underground. We have caves forming. And then remember, what happens to Rangelia is it smashes into the coast of North America. And that's a rough and tumble event, right? It builds mountains like Mount St. Elias, Mount Logan. There's a lot of faulting. There's a lot of uplift. There's a lot of tilting. And Ed's supposition is that the caves that form in the midst of that mountain building event, and with all the pressure of the overlying rock, they collapse and they break apart and they form breccias, which is just, it's like rubble. Think of like talus, but it's deep underground. So you had caves that collapse and you have this rubble that's very permeable because all the rocks are broken and angular and they're all piled together. So that's a good place for fluids to circulate. So that's where we are in this picture right here. And then this is the main thing that I want you all to know, because for years it mystified me until I actually looked at this and read this paper. Now I get it. I always thought, how can the copper have come from the basalt and then ended up in the limestone when the limestone is above it? Like, how do you do that? How do you get copper to move upwards against the force of gravity into the limestone, which is where the mining occurred? It's in the limestone, not in the basalt. This is the explanation right here, is there's a lot of faulting. If we go back there, see, all of those lines are faults, all those blue lines. This mountainside is rife with faults. They're not all active. A lot of them are dead, meaning they're not moving anymore, but it's all broken up. And those faults moved the rocks relative to each other, and this is what you need to do. If this fault moves this rock body up and this rock body down, now you have the greenstone sort of relative to the force of gravity. It's above the limestone now. And where you do that, you have a mechanism to inject these brines. This is just hot, mineral-rich groundwater that's circulating through this 100 part per million greenstone. You have a mechanism for it to flow downhill or down some hydrologic gradient into this broken up, highly permeable area. That's an easy place for the fluids to go because it's really permeable. And then some magic happens that I call geochemistry, where the brines interact with that Sabkha limestoney stuff and deposits or precipitates out copper into the limestone. And it doesn't do it like everywhere in the limestone. It does it right at the base of the limestone, because that's where all of this copper-rich brine is coming from, is from the greenstone. So the very basal layer of the limestone gets injected with these brines, but not everywhere, only where this faulting occurs. So those of you who know this valley well have maybe traveled around to some of the other valleys here. You've gone up to Donahoe, you've gone over to the Glacier Gulch over by Hidden Lake, you've gone over to Nikolai Plateau. You know that there's a lot of places you can go where there's old mining and prospecting equipment littering the landscape at the contact zone where they were looking for copper. And in almost all of those places, they found just a little, and they died penniless and left a huge mess. And that's because you need the geology, the structural geology, the faulting and the tilting to get that perfect situation where the brines will flow into the limestone and precipitate out the copper. And so where did that happen really well? Right here. And so this was where the really sort of valuable outcrops were found. This process, like steps 1, 2, and 3 were happening all over the place, but step 4 is the key one that makes it economically viable to mine it. There might be some other spots like that under the glaciers, and as we'll discuss, those might be exposed in the near future. But for now, it's a pretty unique geography where all these steps occurred and you could form the copper. The one piece of the sort of geologic history, there's a lot of pieces I've ignored, but the one remaining sort of big piece of this valley is, of course, we're in the Wrangles, they're volcanic. Mount Blackburn's a volcano, all these big volcanoes around here. So what's their role in the geologic history of this place? Well, let's talk about that. So this will be pretty quick, but you know, all the little dots, those are mud volcanoes, which are like the Wrangles equivalent of hot springs, which is pretty disappointing. And then these are like the modern volcanoes, right? We've got a few down there. You guys see where we are. There's Mount Blackburn right there. And we have volcanoes of different shapes and sizes. The volcanoes here are complicated. They're not all stratovolcanoes, which classically look like this, like that. And they're not all shield volcanoes, which normally look like that. And that's because of different lava types. We have this kind of weird mix of different kinds of volcanoes here. But we have a bunch. And so I mainly just want to focus on like, well, why do we have volcanoes and what are they doing? Well, we have volcanoes fundamentally because of that subduction zone, right? We talked about that. But we also talked about the fact that the subduction zone is a little clogged up right now by the Yakutat microplate. So if you look at the volcanoes that we can see, and by that I mean the ones that are actual mountains, because a lot of volcanic rocks that you could date are older around here, but the mountain that they formed as a part of is gone. It's eroded away. So we can see a deeper history of volcanism by looking at volcanic rocks. But if you want an actual volcano, a mountain made of volcanic rocks, this is most of the ones, the major ones anyway, that are around here. And you can see they're not that old. All of these volcanoes, the oldest one in this list is only about 4 million years old, which is much, much, much younger than the arrival of the Wrangellia microplate. Remember, that was like 100 million years ago. So these are young relative to the other bedrock in this area. And they're associated with the subduction zone. They have risen up through the Wrangellia rocks. So that layer cake of different layers of basalt and limestone and etc. There's a bunch on top of that too. These welled up, the magma welled up from below and burst out through weaknesses in that rock. So they're younger, they came from below and they've emerged on the surface of what was already sitting here, which is the Wrangellia layer cake. Okay. If this is a lot to absorb, and most of it I don't really care about, but here's the Kennicott Glacier right here. And what I want to show you, this is showing ages. These are all millions of years, all these little boxes. Ages of volcanoes or volcanic rocks, actually the rocks literally, that have been dated around here. And a couple things to notice. One is they generally start older here, like 10 million years ago, and they get younger as you move northwest towards Mount Drum. Oddly, the most recent eruption we know of in this area was at Mount Churchill. That's a bit of a mystery, I think even to the volcanology community. But I'm not going to focus on that. The other thing I wanted to say is if you look at the ages, again, there's Mount Blackburn. It's just off the map, but those rocks are around 4 million years ago old. We just looked at that. And I want to point out that there's igneous rocks in Porphyry Mountain above McCarthy down there and Fireweed Mountain over there, that these were not volcanoes. They didn't, by igneous I mean the rocks formed from magma, but they didn't make it to the surface. So they didn't erupt as volcanoes. The sort of most famous igneous intrusive rock would be granite. You know, it's formed from magma, but it didn't erupt at the surface. It cooled and it hardened within the earth. That's what the rocks of Porphyry Mountain, literally the porphyritic dacite there. And there's a little bit of that same stuff and related stuff on Fireweed Mountain. Those aren't volcanoes, but they're rocks, they're igneous rocks that were sourced from the same place at about the same time. So the rocks of Porphyry and Fireweed Mountain are similar in age to the rocks that formed the eruption of Mount Blackburn. And if you look, this is just a photo. It's a little kind of hard to see. It's kind of like an abstract painting, but this is a section of that beautiful face of Fireweed Mountain that you look at from McCarthy. And the dark rocks are mudstone. Those are sedimentary rocks. But these white intrusions that form these like veins in there, those are all felsic dikes that were sourced from the magma coming up around the same time that blew up Mount Blackburn. And these rocks over here, I think, are porphyritic dacite, the same stuff that makes up Porphyry Mountain. But they intruded into this mudstone. So that's part of the layer cake. There's the mudstone sitting there, and then there's subduction, there's a lot of magma coming up, and it's going to erupt out of the ground in some places. That gives you a volcano. In other places, it's just going to get right into the layer cake and stop there and cool and harden. And if you go up on Porphyry Mountain, which is mostly porphyritic dacite, you'll see little blobs of this black stuff just right along the ridge lines. And that's more of that mudstone that's been cooked. The reason it's still there, it's pretty weak rock, but it's been metamorphosed by the intrusion of this magma. This magma cooked the mudstone around it in these magma chambers and made that rock harder. And so that's why you see that mudstone up on the ridge lines, because it's actually pretty resistant to erosion. So that's what the black rocks exposed on some of these mountains around here are. Just a couple other things to say. Why aren't the volcanoes here erupting? You hear about volcanic eruptions all the time down in the Aleutians. Well, it's complicated, but the basic story is this. We talked about this, that here's the Yakutat microplate approaching North America from the south. That's plate tectonics right there, right? And then it collides. And what happens to your subduction zone when you clog up the subduction zone? You make the melting and the eruption of volcanoes more difficult, more complicated. It has an impact on the subduction zone and on the generation of new magma. And so the volcanoes in the Wrangels are still, in a geologic sense, active, like we had an eruption like 700-800 years ago from Mount Churchill, but they're not popping off all the time like out on the Aleutians because of this story with the Yakutat microplate. Okay, so unlike what I was just saying, I don't really want to do a whole like story about like how glaciers work. There'll be a tiny little bit of that, but I mainly want to share some data, facts and figures, some knowledge about mainly these glaciers right here, because I think a lot of you get questions like that, and there's some numbers. So we'll do a little bit of sort of explanation here, but a lot of it is just trying to share this and yeah, I can give a copy of this PowerPoint to anybody who wants the numbers or whatever. But first of all, let's just, again, facts and figures. This is a helpful number to have, at least order of magnitude. How many glaciers are in this park? Over 3,000. How many kilometers squared? I'd never remember that number, but a lot. 29,000 square kilometers of ice. Of course, that's all in this park. If you look at all the parks in Alaska that are glaciated, there's all of these. There's about that many glaciers. You can see we have a little less than half of them. And And that number is a small fraction of how many are in the state. And when I say the state, I mean Alaska and adjacent Canada, because a lot of these glaciers go into Kluane and there. But even though there's a lot of, we have just, what is that, like, you know, a third or somewhere between a quarter and a third of the glaciers in the state. We have about half the ice in the national parks, 43,000 compared to 86,000 in the state, kilometers squared. But by far the glacier heavyweight, as I like to say, is Wrangell St. Elias. And if you were to look at the glaciers in the lower 48, I mean, there are like a handful of glaciers in Glacier National Park or in North Cascades or what have you. So we have a lot of ice here, and those are some numbers. Simplest way to look at glacier change is to just look at the boundaries of them on a map and, you know, digitize polygons around the glaciers and then look at how they change over time. That was done in about 2014. And this is showing all of the parks. These are these weird Park Service abbreviations. So we're Wrangell St. Elias, you know, Denali, and so forth. This is how much glacier area in each of the parks at two different time intervals. Just, we'll say map date. That's basically when the topos were made, the 50s, 1950s. And then this is the most recent satellite image in the early 2000s. So it's about 50 years of change here, from the 50s to 2000 something. And the consistent pattern here, of course, is that they're all shrinking. We're losing glacier cover in all the parks. And for that time interval, that 50-year period, we're looking at like 8% shrinkage of the glaciers collectively in the parks in Alaska over those 50 years. Okay, so that's a number, 8%. Yeah. Now, this a version of that study was redone and finished last year. This is the data set right here. This was done by some other Park Service colleagues along with some folks down at Oregon State or University of Oregon. And this is overall glacier area. It's a little bit different data set. They did this was automated. The first study I showed you, people were like pointing and clicking on the map. This study was using you know, computer algorithms, not exactly artificial intelligence, but something close to it. I'm sure the next iteration will be AI. But it was automated, so it didn't perform well in some areas, like the Brooks Range you can ignore, and like out in Aniakchak. So this data set's not exactly comparable, but it was done very recently, and so I just want to show you that this is the kind of bottom line that's represented by that graph right there, is over the 35 years that is more recent, from 1985 to a couple years ago, how much ice have we lost? It's a shorter period. This is only 35 years, not 50 years, but it's a more recent, it encompasses a more recent period, and depending on where you look, 12 to 15%. So this is an updated number. It just is, I'm going to get back to this with some other data. The glacier shrinkage is accelerating. Okay, no surprise probably to most of the people here, but it seems useful to know. I used to think it would be useful to know because it would motivate people to change their behaviors. I'm not so sure of that anymore, but you know, we can maybe talk about, is it good to know? Is it worth it? Probably people in this room would ease my cynicism about that. But when we're talking about shrinkage of glaciers in the way I was just describing, which is the area loss or area shrinkage, one thing you have to recognize is it's maybe not the perfect measure of glacier loss or glacier shrinkage, because a lot of the glaciers in Alaska are debris covered, especially at their terminus, and the terminus is where typically a lot of the melt occurs. And so, for example, this is the Kennicott Glacier in 1938. This is a picture taken by Brad Washburn. Just fortuitously, the last year the mines were open, which is interesting. So you can see the bustling metropolis of McCarthy there. And I'm going to show you a picture in a moment of this same area in a modern photo. I'm trying to make 2 points here. One is this terminus area is going to shrink more slowly than you would otherwise expect because it's covered with all this rock. We can map out the terminus retreat. Here's the lake and the other lake, and McCarthy's down here, and we can look at the dates. So here's, just to remind you, most of you know this, here's what the terminus of the Kennicott looks like now with these lakes that are growing rapidly bigger. This right here, if you didn't know this hill right here that is on either side of the main channel just to the north of the footbridge, that's the 1860-ish terminal moraine of the Kennicott Glacier. That at the most recent peak of the Little Ice Age advance, about 150 years ago, that's where the glacier got to. And this lake is impressive, but it really hasn't, the ice margin hasn't retreated that far from that moraine in 150 years. And my point is that glacier area is therefore, it's sort of an imperfect way of measuring glacier retreat or glacier ice loss, because it can be sort of confounded by these sorts of factors. Okay. It's also, glacier area is not a good way to measure the impact of glaciers on sea level rise, which is a big reason we care, about glacier loss because we recreate on glaciers or around glaciers, and we think they're neat, and seeing them change is neat and sometimes disconcerting. A lot of the world cares about glaciers because they're a water supply and or they're in coastal areas where sea level is rising. And so the loss of glacier area is not nearly as relevant as the loss of glacier volume. Like when you lose ice by thinning, that's a direct measure of the contribution of a glacier to sea level rise. And I just want to show you, this is kind of it's a complicated map with a lot of data, but it's pretty straightforward. Each of these balls represents the total mass change of a region, a glaciated region on the planet. There's the whole planet. I should say this does not include the Antarctic ice sheet, and it does not include the Greenland ice sheet. So we're just looking at glaciers independently of those two big ice sheets. And the size of the ball is the total contribution, you can think of it this way, since the early 60s of that area to sea level rise. And you can imagine that the contribution to sea level rise is a function of two things. It's how much glacier do you have. If you don't have much ice, you can't contribute a lot to sea level rise when your glacier shrinks. And it's a factor also of how fast your glaciers are shrinking. So if your glaciers aren't changing, it doesn't matter how much ice you have, you're not going to create sea level rise. And so the color, the red represents areas that the ice is shrinking faster. It's losing mass more quickly. And again, if you multiply that rate of shrinkage times the amount of ice you've got, you get the total change. And what I want you to take from this is that up in Alaska, ALA is Alaska and adjacent Canada, we have the biggest ball. These are big numbers relative to how much ice there is on the planet. We've got the Himalayas, we've got Arctic Canada, we've got a lot of places with a lot of ice, the Alps in Europe, etc. But these figures come from this kind of data. And since 2006, Alaska's been contributing over 20% of the total contribution of glacier shrinkage to sea level rise has been coming from here, from this area, not just from the Kennicott Glacier, but that's out of proportion to how much ice we have. It means we have a lot of ice, but it's also shrinking very fast. And that matters. So why are glaciers shrinking? I promise not to give a glaciology lecture, but this is the basic sort of way that glaciologists think about glacier volume change. Is a sort of little hypothetical glacier here. There's the mountains, there's the terminus, McCarthy's over here. Up there it's cold and it snows more, usually. And down low, it's warmer, it snows less. Usually we have some debris cover. And a glacier that's in equilibrium with its climate, the amount of new snow that turns into ice would balance the amount of ice that melts down in the terminus region. And so you'd have this constant flow of new ice from high elevations down to the low elevations where it melts away. And again, if it was in equilibrium with climate, the balance between accumulation and melt would be, they'd be equal. And that glacier wouldn't be changing shape and size. It wouldn't be contributing to sea level rise. It would still be melting because you have new ice forming, melting at the bottom, but the net change would be zero. So we have names for those parts of the glaciers. The ablation zone, ablation's a fancy word for melt. Accumulation, we mean snow that's going to turn into ice. There's other forms of ablation. I'm not going to say much about that today, but like icebergs calving off of glaciers into the ocean or into a lake. That's not melt, strictly speaking, but that's part of the story. Like I said, I'm not going to get into that, but we have a couple ways we can measure, more than a couple, mass balance to sort of try to understand this shrinkage of glaciers. One way is you can go up on the glacier and make actual measurements of the winter snowpack and of the melt that occurs in the summer. We do that on a couple of the big glaciers in southern Alaska in the parks, the Kennicott Glacier, that's this one, and the Kahiltna. We have weather stations and we have some measurement sites on these glaciers. And you might think, well, gosh, it's surprising the glaciers are shrinking right now because we've had some big winters, right? And we've had good winters in southern Alaska lately. And that's part of the picture. This mass balance is partly about snowfall, but it's also about melt. And making measurements like these allows you to parse those out. Are the glaciers shrinking because it's snowing less, or are they shrinking because it's melting more, or some combination of the two? And without getting too into the details, I'll just show you some measurements from the Kennicott Glacier. Again, this is just showing, it's not rocket science, far from it. It's hard to do, but it's easy to understand. This is just showing a relationship between summer temperatures. We add them up in this weird way called positive degree days, but a summer with a lot of warm days would have a lot of positive degree days, and a cold summer wouldn't. Then the amount of melt that occurs, this is melt of meters of snow water equivalent, which is if you took ice and or snow and just melted it, how much would you get? That's kind of the way we equate melt of snow and ice to one figure as we do it in terms of snow water equivalent. And you can see these are negative numbers right here. So the lowest dot right there, that's 6 meters of snow water equivalent melted in the course of one summer when it's a really hot summer. Okay, so this is what you would expect. When it's a really hot summer, it melts a lot. If you do more work with these numbers than I'm going to show you, and this has been done at a lot of glaciers, what you find out is, why are the glaciers shrinking? It's not, the dominant effect, especially in Alaska, is not changes in snowfall. It's hot summers. We get hot summers and the melt is exceeding the accumulation, even in these big years where we get a lot of snow, and the glaciers shrink. So that kind of work lets you parse out the difference between accumulation and melt. But then there's another way that's, sexier and lets you do that kind of work on a lot more glaciers at one time. This is measuring mass balance by looking at change over multiple years in the actual size of the glacier, measuring it directly. And we're not talking now about measuring the outline of the glacier, we're talking about measuring the surface of the glacier thinning. That's where volume change, where mass change occurs. And the way you can do that is fly a plane like this one. There's a little cartoon plane equipped with a fancy GPS unit and a LiDAR, which is just something that shoots lasers, points out of the bottom and measures the time it takes them to get back to the plane. You put this instrument package on that plane and then fly over a bunch of glaciers. And that'll tell you, won't tell you about melt versus accumulation, it'll tell you about the net. Like if it snows, it melts, it snows, it melts for a few years, and you make those measurements at the beginning and at the end, you can say something about how much mass the glacier lost, or volume, they're interchangeable, over time. And so I'm going to show you some data from that. You can also do it with satellites, which has pros and cons to it. So just to give you a sense of what that data looks like, and then some sort of summary figures for the Kennicott. And for the Wrangels, this is the Wrangell Mountains right here. Okay, so there's the Kennicott Glacier, Nabesna Glacier, there's Mount Drum and Mount Sanford, Mount Wrangell. And these are all color-coded. These are all the glaciers in the central Wrangels. This was done with satellite data, not aircraft. And it's showing you for any given point, so let's look like down on the lower Kennicott there, it's kind of orange and red. And so that means that in that time period, which is over about 50 years, that the average thinning rate was about 1.5 meters, maybe up to 2.5 meters per year. So that's net. Remember, this isn't melt, because accumulation and melt balance out to some extent. This is the net change. So this is how much the glacier surface year by year, every year, these are values of meters per year over that 50-year period. This is how much the surface of the glacier is going down. And it's measured with satellites. So the thing that you might notice is that most of these glaciers are a little orangier or redder in their terminus areas than they are up in their headwaters, and that's typical. The top of Mount Blackburn is still pretty cold and snowy. It's not changing a lot up there. Where most of the melt and most of the thinning is occurring down here. So those values that you measure on the lower Kennicott, you can't extrapolate those to the whole glacier. If you want to know how fast the glacier as a whole is thinning, you have to average those values over the whole area of the glacier. And if you do that, you get numbers like these. And these are sort of bottom line, like how much is the Kennicott Glacier contributing to sea level rise every year over a given time interval. And so, for example, over that 50-year period, that's the same 50th year, I don't know why it's 5 there and 7 there, but if you average it, the Kennicott is thinning by about, over the whole glacier, 20 centimeters a year, 21. That may not sound like a lot, but imagine a swimming pool the size of the Kennicott Glacier draining 20 centimeters every single year. And that is the right way to think about the contribution of the Kennicott to sea level rise. The Wrangels as a whole, if you take all of these and average them, you get a pretty similar number. So we're still in the like 20 centimeters range. Using different techniques over a slightly more recent time period, a little bit higher number. Close to 0.5 meter per year, so something like this. Why would that number be higher? Well, probably a few different reasons, but a big one is that when you look at all of Alaska, you're also including a lot of tidewater glaciers that have the capacity to shrink much faster for reasons that include the calving icebergs and all of that sort of thing. But this is a direct measure of contribution to sea level rise. This is the sexy aircraft-based data. So this is, I'm just saying sexy because I always thought Paul Klaus and Ultima Thule were like the coolest thing in the Wrangels. And he's been the pilot for an awful lot of this flying. These data I'm going to show you here, the next couple slides, are from Operation Icebridge. This is a NASA-funded project that paid for Paul and other pilots to fly glaciologists, mainly from the University of Alaska, around with that radar unit. And I'm showing you which glaciers in the Alaska parks, I'm not showing the ones outside the parks, but I could, are ice bridge glaciers, meaning that every few years for over 20 years in a few cases, they've been flying over the center lines of these glaciers with that LiDAR and measuring change rates. And you can see that if you look at glacier numbers, the dark red is the ones they actually flew, and the light red is how many glaciers are there in the park. And it looks like they didn't fly that many glaciers. But if you look at the dark red up on, like, let's say Wrangell St. Elias, you're like, that looks like a lot of glaciers. What it is they selected for the biggest glaciers. So if you look at glacier area, they flew most of the ice in the park, even though they didn't fly most of the glaciers in the park. They skipped the little ones, if that makes sense to you. So I just want to show you data from one glacier, because, boy, we could be all here all night. The Kennicott again, because this is the one that we've been focusing on. So this is, compared to the satellite-based data, it's very, very accurate. That's a neat thing about these numbers. There's a lot here to digest. but it's telling us a real story. So first of all, let me just walk you through this. Here's a map of the Kennicott Glacier. There's the route. You can see their flight tracks in every given year. The numbers, they might be hard to read there, but they're the same numbers as here. So the earliest track was in the year 2000. That was the first measurement. The last one, 2021, in blue. And these are color-coded the same. So they're stacked on top of each other. There's the blue one, last year or 2 years ago's flight. And the earliest flights, like 2000, they were much narrower because they used an older-fashioned instrument. But anyway, this is showing, so, they didn't fly on the Root Glacier or the Gates Glacier. Yeah, so you can tell that now. It's okay. Then I guess I'll show you what are we seeing here. This is glacier elevation. So the terminus is here. The top of Mount Blackburn is over here. And you can see that they didn't make any measurements on the uppermost part of the glacier. That's up here, all these high elevations. Probably a few reasons, including they would have crashed into the mountainside. But also these numbers get really messy when you get into really steep terrain. So they basically flew the flat valley floor. You can see this faint line right here. This is the area altitude distribution of the glacier. So what you can see is that from this elevation up, from about 3,500 meters up, there's very little area because that's just the very mountaintops. And so you can get a sense that their measurements include most of the area of the glacier, but maybe this zone, it would be nice to know a little more. Up here, there's not much area to influence the results. This is how many, basically the area that was measured. It's a logarithmic scale. So how many pixels on a computer screen were measured? These numbers here, 10 to the 2, that's like 100 pixels per 10-meter elevation bin. Basically, that's just telling you that was the old days when the glacier lines were pretty narrow, and then they got a lot more measurements in the subsequent years because they got a fancier machine, a fancier LiDAR unit. And then this is the results. And so what you're looking at is from the terminus up to, well, that high, up by that's Pack Saddle Island right there. So from the terminus up to Pack Saddle Island, at any given year, what was the surface elevation of the glacier, measured very carefully with a LiDAR. And so you can see, well, I should say, this is all measured relative to an arbitrary number. So like, what is 0 on this graph? It doesn't matter. What you want to look at on this is the change from one measurement to another. And so, for example, down here by the terminus of the Kennicott, this is like minus 25 meters, and that's about 40 meters. So that's the blue is 2021, the pink is 2000. What you're seeing there in about a 20-year period is about 65 meters of surface thinning on the glacier. Meaning, that's over 200 feet, or it's maybe very close to 200 feet. That means if you pitched your tent near the terminus of the Kennicott in 2000, in the year 2000, and just stayed there, well, you'd get a little pedestal under your tent and then you'd fall off the pedestal, but you would end up over 200 feet lower in that 20-year period. And I think I like to look at this data this way because measuring it in meters per year has a tendency to make it sound like a small number. And I've been here since 1990. That's 10 more years than the duration of this. And when I look down from my house at the terminus of the glacier, I see this. I can't see, 1.5 meters of thinning per year. I don't have the eyes for that. It's difficult to detect. But when you start talking about 200 meters of thinning, or even more, and some of you have been here longer than me, and many of you will probably end up being here longer than me. These are big numbers, and these measurements are very, very accurate. So the usual sort of like, well, there's errors, and who knows how this is good data, and so What you can see that's relevant is in the upper elevations, the changes get quite small. And again, we've talked about this, that you get most of the melt down by the terminus, not up at the top. But these numbers confirm what I showed you in some of those early figures about the thinning rates of the Kennicott Glacier. So I just wanted to show you that. We have that for most of the glaciers in the park. What about the future? Well, we don't know. It depends on a lot of things, including what we as a human society do. But these are projections from the different parks, Aniakchak, Denali, Gates of the Arctic, all the way on down to Wrangell St. Elias. So that's us. Predicting based on a fairly modern and sophisticated glacier model that takes into account glacier dynamics and mass balance, what our glaciers might look like park-wide by 2100, so 80 years from now, 77 years from now. So each of these plots goes from 2015 to 2100. So the right-hand side is the turn of the century on all these. And what they're showing is how much mass is remaining of all the glaciers in the park relative to the amount of mass we had in 2015. So they all start with 1. So like however much ice we had, that was 1. What are we going to have at the end of the century? And some of these are pretty easy to interpret. Aniakchak, Gates of the Arctic, Klondike Gold Rush, even Lake Clark, almost none. Almost no glacier ice remaining in those parks by 2100. There's different colors here, and those represent different choices we make as a society about how many greenhouse gases we emit. And the paper that this data is abstracted from had in its title, "Every Degree Matters." And that's because there is a difference between, let's say, the blue line there for Katmai National Park and the red line. And those differences, these are different projections of human behavior and how much emissions we collectively put out. And so they do make a difference, but nonetheless, you can look at the cloud of projections to get an idea. And one takeaway from this is that Wrangell St. Elias, this park uniquely, will have a significant amount of ice left by the time some of us are dead, and many of you will survive to 2100, I'm happy to say. And this will be one of the few places in Alaska with a significant amount of glacier cover remaining. Not the only place, but the story is decidedly grimmer for many of these other areas. Why does Wrangell St. Elias retain so much ice? Because our glaciers are huge. It's the basic, simple answer. It takes a long time to melt away a lot of ice, even in a warm climate. And our glaciers are very big, and half of the glaciers we have here is still a lot of ice. So they're not all going to go away, but this is a sobering prediction for the future of Alaskan glaciers. If you want to look more broadly, this is data or results from the same paper looking at Western North America up to Alaska. And basically it's using this same scale. 1 is all the ice is still there, and the hollow white circle is all the ice is gone. And this is not just for the parks, it's for all the glaciated areas in Western North America. And so, there's North Cascades and the Olympics and Southern British Columbia. What you're seeing is essentially no ice remaining. There's Wrangell St. Elias, that's probably like the Malaspina Glacier. This is where the good news is, where a lot of the ice remains. The St. Elias ranges in Kluane, but even in Alaska, we're looking at a lot of loss. And so this does not have to be the future. It can change, but I'll reiterate what the message of the paper that produced these results is our decisions will affect this. When people ask you, when will the Kennicott Glacier be gone? Do not tell them soon, because it's a really big glacier with a really high mountain at the head, and it's going to be here a long time, but it's getting a lot smaller. It's big enough that it can get a lot smaller and still be a big glacier. And so that's going to be the story here. A lot of places have smaller glaciers and they're going to go away sooner. Okay, so the rest of this is just some fun facts and figures. There's really not much left. This is just a Landsat time lapse of the Kennicott Glacier flowing over like a 40-year period, I think, maybe 50, just to convince you that even down in the debris-covered ice, it's moving. You got to watch it pretty slowly, or watch it over a long period of time to actually detect it. If it wasn't so late already, we'd talk about the Deborah number, Ben, Sally, but we don't have time for that. So just some like numbers. People always are curious. Well, how deep is the lake out there, right? There's the lake up there by the, where people go and camp out. And here's the main lake down by the footbridge. And we measured that a few years ago. And the kind of numbers you get, like maximum depths for the eastern lake, 60 meters deep. That's pretty deep. Maximum here, about over 70 meters deep. And these all of this like garbagey weird stuff, that's just where ice was still remaining in the lake, and so the data got messed up. The trend is pretty clear that it gets deeper and deeper as you go upstream. It's an over-deepened basin, meaning as you go up, it gets deeper. And so those numbers are almost certainly out of date, and the deepest depths are deeper now because the ice face keeps retreating. So there's a lot of ice and a lot of water. A question I get a lot, and for a long time I couldn't answer it, was how thick is the ice? And of course it's different everywhere, so there's no one answer. But some colleagues from the University of Arizona and University of Alaska Fairbanks flew some radar. This is ice penetrating radar that can see the bed of the glacier from an aircraft, and shared that data with us. And so this is a map just of the lines that they flew, so back and forth with an airplane. And the color scale there, kind of ignore it because it's not the same as this one. But basically this is just to show you the measurements here are interpolated and extrapolated from this data set. So they're most accurate in the center. They're the least accurate on the edges, but at the very edge we know the thickness, it's 0. So you can interpolate from 0 to these depths and get a pretty good map of what the bed of the Kennicott Glacier looks like. And that's this. So these are ice thicknesses ranging in, the data don't really go beyond here because they didn't make measurements upstream, but you can see that the deepest ice, or the thickest ice, in this view where that's Donahoe, is up to about 500 meters thick, 1,1700 feet, something like that. And then of course all around the edges it goes down to 0. A couple places that you might be interested in, if we're in Kennicott here and we look straight out into the, not the very edge, if you look at the very edge, the ice is 0 meters deep, but just less than a kilometer out, there's a pretty deep area right there that's about 375 meters thick. So looking out from the Kennicott Glacier Lodge, maybe a quarter of the way across the ice, that's a thickness that you can talk about. And then this is right where everyone goes on the Root Glacier. This is right where you get on the clean white ice and walk around and go ice climbing. The thickness is there, again, not right at the edge, but once you're out onto the ice proper, it varies, but around 300 meters thick. So there's some numbers. That's kind of good to know. Soon, right, Jamie? This will be in the visitor center right down here at the Blackburn School. This is a physical model that was made of the data I just showed you. There's Fireweed Mountain and Bonanza Ridge. This is made from really high resolution LiDAR data on land, and then the radar data in the glacier bed. There's the airstrip. And here's where the modern lakes are, there and down there. And so you can see, because this was carved into plywood, this deepening and they're like contour lines, even though they're really just plywood, plywood layers. What I want you to take note of is that really deep ice, or deep lake I was showing you a few minutes ago, is like here and here. So as the glacier retreats, the lakes are just going to get deeper and deeper and deeper and deeper and deeper, all the way as far as we have measurements. it's reasonable to think that the Lake Kennicott will reach to Hidden Valley eventually. The bed is deep enough at least for the water to go to there. And going back to the question that was asked earlier about the Nizina, at some point this lake will be deep enough that the ice will float in it, and that will make it much easier to break off large tabular icebergs and speed up the retreat of the glacier. This model, which will be at the visitor center, also has an epoxy glacier that sits in it that you can take out and put back in. And then it has the 1938, it has the Washburn Glacier, the 38 glacier, as an additional shell that sits on top of that. So you can see the 1938 glacier, the 2018 glacier, and then this, which is, I don't know, the year 2200 glacier, something like that. Just a couple things about velocities, just to tell your guides. These are measurements from Billy Armstrong. He published these in a paper down in this is this terminus area, the Kennicott. It's in kind of early spring and then early summer. You can see this is the velocities here going from not moving down to about a half a meter a day in pink. Not much motion in the late winter. More motion, so it speeds up like a lot of glaciers do in the early summer. And what do you get? You get speeds up as you're going up towards Hidden Valley of up to about a half a meter a day. Those are not typical on the route where you walk out on the clean white ice right there. Those numbers, 15 centimeters a day, 20 centimeters a day, less than a foot a day. But those are kind of typical numbers for the summertime. Lots of details to that. If you want to know more about how fast it goes during the Hidden Lake flood, talk to Tim back there. He can tell you a lot about that. But it does get a lot faster up in the ice fall. These are measurements that were, I should say, an analysis that inferred the speeds it's kind of globby, it's hard to see what you're looking at, but this is the stairway ice fall and velocities that were measured there. And these bright yellow colors, again, summer and winter, so a little bit different pattern, although not that different. We're getting speeds up to 3 meters a day in the stairway ice fall. And that makes sense. It's like a rapid, right? It's like a river. It's quite thin there. It's quite steep. It's moving fast. That's about as fast as you're going to see, more or less, for a non-surging glacier. Those are fast speeds. And not typical of the rest of the glacier, but you do find those in the ice fall. Here's a map of the central Wrangles, and just to look like, broadly speaking, there's the Kennicott and the route. What are typical numbers? I think the most common number is yellow, and about 0.4 meters a day. I kind of think this way about glacier velocities. If I'm on a big Alaskan glacier and I'm not at the terminus, and I'm not way up in the accumulation zone, it's probably going about a half meter a day. That's kind of my rule of thumb if I don't know. And this maybe that's a little bit of an overestimate. This would suggest that 0.3 to 0.5 meters a day is typical. But here, to get those kind of numbers, remember, you got to go up by Hidden Creek Valley or up towards Stairway Ice Fall, and you'll start getting speeds like that. Some of the fast ice you're seeing here, those are surging glaciers. I'm not going to talk about that at all. And I'm tempted, I'm going to stop because there's just a little more about some other stuff, and I think it's been 2 hours. I'll just stop and see if anyone has any questions. That's enough for one day, don't you think? Yeah. Thank you.